So in the last video, I went over how to create your OpenRocket file for beginner rocketry. However, your rocket design itself is still incomplete because if you followed along with the tutorial and use the same numbers as I did for the nose cone and the fins, your stability number is 4.95%, which is unstable. First, an unstable rocket in flight will tumble and crash. It could potentially hurt someone, and you will also fail your certification attempt. So we want to aim for a stable design. So a stable rocket, we're aiming for 7% stability here. When you look over here at the stability number, 7% will be a stable design. You could do that by changing your nose cone and fin parameters. In this video, I'll focus on the fin parameters and also the fin CAD. So if we edit the fin, we'll see that we can change the root chord, tip chord, height, and sweep length. These are the parameters that determine your fin shape and also the parameters that you can change to get a stable design. So in Inventor, to CAD your fin, just open a new Inventor part, start a sketch, and start off by making the fin tabs. So our fin tabs have a set length of 6 inches and a set height of 1.395 inches. Okay, so in OpenRocket, I chose a trapezoidal fin, and that's what I'm going to be modeling in Inventor. To make that, we'll just create an arbitrary trapezoidal shape. So for the offset, we'll create a horizontal line. And then any angle line, it doesn't matter. We'll constrain it shortly. For the top, also another horizontal line. And then we'll go over to the other side of the fin tab, a horizontal line, and then connect it to the top. That's the trapezoid. Now we want to add these parameters, the root chord, tip chord, height, and sweep length in Inventor. We can do that by going to the Manage tab up here and clicking Parameters. We're going to add a numeric parameter, add numeric, call it the root chord. We're going to add the tip chord, the height, and the sweep. I misspelled that. Sweep. So in OpenRocket, I had these set at 7, 3, 3.5, and 3. Now to add those parameters to the sketch, we're going to use the dimension tool in the sketch menu. So click on dimension, and let's begin. The root chord is the distance between this front point right here. As you can see, it's highlighted green. It's this front point to this back point right here. So the dimension should look something like this. You can click and then type in root chord. An inventor should already recognize this as a defined parameter. Make sure to spell it correctly. If not, and if it doesn't recognize it, it's going to be red in color. Press enter. It looks a little funky right now, but we'll fix that momentarily. The tip chord is the length of this horizontal line up top. So we type in tip chord. The height is the distance between the tip chord and the fin tab. So this line and this line. That's your height. And the sweep is the distance between this front point and the front of your tip chord. and it's the horizontal distance. So this is your sweep. Okay. So as you can see, it's still wonky, and that's because we have set our fin tab in an open rocket to be in the center of the fin. You guys can change this, but make sure that when you do change this tab position, that the fin tabs does not exceed the root chord itself. So you wouldn't want a fin tab that's too far. See, like this. This would not be an acceptable design because your fin tab is going is offset from the fins itself. I'm just gonna keep it at 0. So it's centered. Um, if we have our fin tab as centered, we can actually change or dimension our overhang with the equation root chord minus our fin tab length, which is 6, divided by 2. That's for a centered fin tab. If your fin tab is not centered, if it's not centered, you will actually have to manually input the overhangs that you guys have. If you're having trouble with that, talk to one of us. We can help you with it. But mine is centered, so I'm just gonna keep the equation, and that's a fin design. Now we could finish our sketch. Click on the extrude tool and extrude our sketch to a distance of 0.2, which is the thickness of our fin. And that's the fin cat done. Now the benefit of doing it parametrically like this is if we were to change our fin tab dimensions. Ignore that. If we change our root chord, tip chord, height, and sweep length, we can do the same in Inventor, and our CAD will match our Open Rocket design. So if we go to Manage and Parameters, I'll go back to Open Rocket and change it to a completely different looking fin. This is a horrible fin design, by the way, guys. This is just for demonstration purposes. Even Open Rocket is yelling at us. But I changed my parameters. It's 8, 5, 2, and 7. I can go back to Inventor, input these. And our CAD matches our Open Rocket design. Like I said before, we are aiming for 7% stability. The main things that change or that increase our stability for the fins is the root chord, tip chord, and height. The sweep also has a factor, but these impacted the most. And out of these, the height impacted the most because stability basically means that the forces, the aerodynamic forces on the rocket, that cause it to rotate or cause a couple moment. If you guys have taken statics, this is your center of pressure, and this is where your aerodynamic forces act. They cause a couple moment about your center of gravity where your rocket rotates. If these forces are too high, your rocket will tumble, and we don't want that, basically. So we want 7% stability. So the location of your center of pressure is dependent on how the air hits your rocket. And because the fins extend farther out from the rocket and have a surface area that directly impacts the air, it actually causes the most change in the center of pressure itself. This is a very simplistic explanation of this. You guys can research it more, but that's the crux. So I'm just gonna go for 7% right now. Okay. So I wanted to talk about this design too, because as you can see, it has reached 7% stability. However, this whenever we think about the rocket coming down on a parachute, our fins actually impact first because it's the lowermost point of the rocket. And a design like this where the fin is almost like a parallelogram has a very thin point out here at the bottommost point, which is a point of failure, right? There's going to be a stress concentration. There's going to be a lot of forces right here, and it might crack. So we do want to strive away from this design. It's not like if you do it correctly, it's a valid design, but we want to strive away from that. So let's change my report up. There you go. And now we have reached 7% stability. It's 8.78, which is higher than way higher than 7, which ensures that yeah, my rocket will be stable in flight and not tumble. Now, because I've changed it here in OpenRocket, I can input these same parameters into Inventor and get our FinCat. So my parameters 75453. And there, my CAD matches my OpenRocket design. Now to submit this CAD, you want to open up your extrusion, click on the plus, and then right click the sketch, and then click export sketch as, and then save type will be DXF, not AutoCAD drawing, AutoCAD DXF. Name it FinCAD again, and save. And that's that. Next video, nose cones. See you.